Another test that's important, and some of you know very much about this and some of you may not, so we cover it, is the Sharpie Impact Specimen. This is a tool to measure the resistance of a material to fracture. High toughness is good. We have a bar that's nominally 3/8 by 3/8 by 2.5 inches long. It has a very carefully applied notch that's put into the bar. That specimen is mounted here in a support with the bar on the tension side. This calibrated hammer has a certain amount of potential energy. When we release that hammer, it slides through, breaks the bar, throws it into this sophisticated collection device, and then swings up. The difference in height of that hammer is indicative of the amount of energy that's been absorbed by that specimen when it fractures. And so again, it loads the specimen rapidly, and it loads it so that the notch is on the tension side. Eventually, most of the samples break. There can be some that are tough enough that they exceed the capacity of the hammer, but most of the time they'll break. And when they break, we measure that energy in foot-pounds. If you measure that energy at high temperatures, you get relatively high values of toughness. If you measure the same material at low temperatures, you get low values. Between the high values and the low values, we go through something called the transition. The transition is characterized or is made over a temperature range, and we typically call that transition temperature. Transition temperatures, like cholesterol, low values are good. So the lower the transition temperature, the tougher the steel is at low temperatures. Of course, conversely, the higher the numbers, the higher the toughness, the lower the toughness of the material at higher temperatures. We've specified toughness on bridge steels and bridge weldments for probably 30 years now, going on 40 years. In the steel business, we've not typically specified toughness. Since the 80s, we've had toughness on the core regions of jumbo sections loaded in tension. They're subject to welding. In the post-Northridge era, we have toughness requirements on the weld metal, and that gets into the CVN numbers. Again, that's buried in the 8 of this particular electrode, and that's required to have 20 foot-pounds at minus 20 degrees. I promised you an easy way to find these properties. If you go to the Lincoln website, anybody can do this. You can download the properties of any of the materials we produce. I'll give you the website address in a moment. What's important in here, we not only give you the performance of our properties, but we also give you the AWS requirements. So if you want to know what AWS requires, well, there are the requirements listed. So it's a really easy way for you to look up and say, well, I'm looking at this electrode. Is toughness required? Is it not required? What's the yield? What's the elongation? What's the temperature at which the toughness is required? And you can get that data. Remember, steel is typically specified based upon the yield strength of the material. We talk about grade 50 material, and that's 50 yield, right? When we talk about grade 70 weld material, that's tensile strength. I won't get into the reasons and whys behind that right now, but that's a point of confusion oftentimes. 70 will be the tensile. Associated with 70 is a yield strength, 58 KSI, and 58 to 50 is about matching, and that's why we consider 70 weld metal to be matching on 50 steel. Okay, these are the addresses I wanted you to be aware of. I think one of the best things going on right now is the AISC Solutions Center. You can call AISC and get answers. You can email AISC and get answers. Somebody asked about the Blodgett book. You can get that from the James F. Lincoln Arc Welding Foundation. That website, jflf.org. A variety of technical articles are on that site. Also, my employer, Lincoln Electric Company, you can go there and download those certificates of conformance I just told you about. Also, we have a field called Ask the Experts or Ask Us, and you can type in your question, and it goes to a whole array of people who get back to you with an answer. One of the things I like best about the Solution Center is they seem to know when they don't know, because I get calls from them on a routine basis. Joff gets calls and they say, we have a question, we want to make sure we answered this right way, what do you think? And so they have a whole array of people they contact to try to get answers. Well, that's a transition point. Are there any questions on what we've covered so far? All right. Well, then let's continue on. I'm going to go through this fairly rapidly. Principles of connection design. I'm going to give you a variety of good practical things that can be implemented in your designs. It really doesn't matter what we make. Connections seem to be the weak point, don't they? When space shuttles failed the first time, where was it? At a connection. Happened to have an O-ring involved, but it was at a connection. And when the seam of my pants tears out, where is it likely to fail? At a connection. Don't sarcastically say it's an overload problem. Okay. So connections tend to be the point of failures. And so it shouldn't be a real surprise to us that when we put welds in connections, welds will be associated with failures. But the failure of weld, more often than not, goes back to become an issue of connection problem. And so we want to take a good look at some principles to avoid connection failure. Principle 1, provide a path for the force to enter into the section that lies parallel to the force. Bill Millick, Bill's still alive. He's still active. He was the vice president of research of engineering for AISC for many years. Bill says the force goes to the stiff part. Now these are both saying the same thing. What is it? Here's an illustration we looked at before. We're going to take a vertical load. We're going to apply it to a lug. The lug's welded to the underside of a beam. The load path is very simple in this. Ultimately, that vertical load is going to go into the web. It's going to go through the bracket, through the weld, into the flange, and into the web. Direct load path. No big challenge here. But what if we rotate that lug 90 degrees? And I trust that you can see that this is a markedly different situation. Because now we no longer have the same load path going directly into the web. It needs to transfer through the weld into the flange and then somehow get concentrated into the web of the section. And so now our weld is no longer uniformly loaded along its entire length. Now we can improve the situation by applying some stiffeners. And yes, it stiffens the flange, but it really provides a load path for that vertical load to enter into the member that lies parallel. When we think about it, we really don't need that welded all the way to the top, or that stiffener to go all the way to the top flange, right? We really don't even need a rectangular stiffener. We get by with a triangular stiffener when we understand what we're really trying to do. We're providing a load path for the force to enter into the member that lies parallel. Or, Mr. Millick, the force goes into the stiff part, and the stiff part is the portion right next to the web. Rotate the beam 90 degrees, and we have a different problem. Does everyone see that that vertical load ultimately wants to go up into the flanges? If that's our resisting element, how much good is this horizontal weld doing? Almost none. Now, if you assume those two vertical elements and the horizontal element were all equally effective, we all agreed that that horizontal element really isn't, then these two vertical welds could be overloaded very easily, couldn't they? I don't care too much of whether you put those welds in there or not, but what I do get concerned about is that you don't plan on those being used in resisting of the load. Of course, you could leave the weld off and save some money and just make sure you proportion out that weld properly. Now, this is not the best example. It's not a practical example, but it actually is very good from a tutorial point of view, and so I'll use it. We have two angles, and we have a pair of transverse welds that have been applied, at least transverse as opposed to the angle down below. And I'm going to assume an unlikely loading condition, and that is you're putting tension between those two angles. Now, I realize that's not very realistic. But now let's take a good hard look at that. If that vertical load comes down through the web of that angle, does everyone see that most of that load is going to transfer through the weld on the left? The fillet weld on the right is going to do almost nothing. So if you assume 50-50 distribution of load between those two fillet welds, you're probably going to have twice the load through the fillet weld on the left than you anticipated. Now let's look at the other orientation. That load's going to come out this stem of the bottom angle. Does everyone see that the length of that weld is not going to be uniformly loaded? Almost all the load is concentrated on the end of the weld. Let's go one step further. By definition, that's either going to be the start of the weld or the crater, right? The welder might not carry the weld all the way out to the end. Or when the weld was struck, maybe the arc didn't strike and we didn't get good fusion at the beginning. If it's the crater, maybe the crater didn't get filled, or maybe there's a little undercut. The point is there's likely to be a workmanship defect there. Now, if there's twice the load on the left weld as anticipated, and if only half of the weld's effective, then you have 4 times the load on the end of the weld. And if you have a workmanship defect to boot at the end, does that connection have a chance of survival? Probably not. So we could harp on the welder who left the undercut there or left an unfilled crater there, but whose fault really is this? The designer or the detailer who put the connection together. And how can we make it better? Well, there's where a stiffener really helps, because now the load path is through the stiffener into the outstanding leg of the angle down below. You say, well, okay, that's not very practical. Let me give one that's a little more practical, and now let's look at a beam to column connection. Let's go back to California on that morning when the earth decided to move, and let's look at a column without a stiffener. Now, when I apply a big tensile load on the end of this beam, what I found happened in Northridge is I tended to get a crack at the center of that weld, and it propagated out to the edges. I trust everybody can see now why it would propagate from the center, because even though the load may be very uniform out in the beam, as I get closer to the connection, there's going to be a peak stress at the center of the width of the weld, because that's directly opposite the web. How can I solve that problem or improve it? Well, that's where I put in continuity plates and now have a more even distribution of load across that weld. Dr. Ralph Richards found for some shapes, not all the time, for some shapes, the peak stress was 4.2 times the average stress. That's in modern steel 10 years ago. This is Kobe, Japan. January 17, 1995. A lot of box sections used in Japan. They had some damage in their steel frame construction in Kobe, but one of the differences were the cracks initiated at the outside edge and propagated in. I trust everybody can see why that is. Even though the loading in the beam is fairly uniform away from the connection, as we get to the connection, the outside edges of the beam are more severely, outside edges of the weld are more severely loaded. And what can we do to even out the distribution of stress? Well, that's where a continuity plate, stiffener, diaphragm are all helpful. Yes, I know those are harder to apply in those situations, but there are methods to do that. So here we see 2 examples where the non-uniform distribution of stress can be explained by not providing a path for the force to enter to the member that lies parallel. Weld tabs. Weld tabs are that auxiliary piece of material on which the weld is started or terminated, illustrated here in purple. Weld tabs are kind of a non-issue in Northridge, but a major issue in Kobe, Japan. Does everybody see why? The weld tabs are in the high stress area. And the termination of the weld, and doing so in a quality way, became a major focus of the post-Kobe investigations. Here's a water tower. You know that tension rod has 2 components of force, a vertical component, a horizontal component. Where's the horizontal component of force going to be resisted? By these outside quadrants of that leg. Does everyone see there's not a good load path to get over there? The failure mode of the horizontal force is going to be a punching or a pulling out of that stiffener, of that connection from the leg. Now, there's not enough force there, it's still standing, it's not a problem, but it's really not a good load path. In contrast, here's a bracket to a transmission tower. And of course, there's the same components of force applied to that angle, but look at that bracket. It transfers the force exactly to the right location. It goes right to the stiff part. What good does this stiffener do in a tubular member? almost none. If we have cyclic loading applied here, you know that that's going to diaphragm that sidewall. Eventually, we get a crack at the end of the stiffener. If you really need the stiffener, and if you need more stiffness in there, there's a good detail to make sure you get good load transfer. Because now the force enters into the member that lies parallel directly. This is a bridge application. About 20 years ago, we had some people that were discouraging the attachment of stiffeners to the flanges. And then that crossed over to not attaching transverse connection plates to the stiffener. And then that resulted in a variety of cracking in the web. We called it out-of-plane cracking. Well, what's going on? We have a moment coming in through that beam, through the bolted connection, into this transverse connection plate. That force here, the couple that results, this force to the left ultimately wants to be resisted by the flange. It sneaks its way through the fillet weld into the web, and now how does it get to the flange? Only by local bending. That local bending eventually results in cracking at that flange location. What's the solution? Apply a fillet weld right up here, and we have a direct load path. Now, I know that that's a Category C detail, and if you don't weld it, you have a Category B detail, but we have to examine our whole system when we select our fatigue categories and details. The absence of that results in cracking. Principle number 2, don't put welds in bending. I'm going to leave our structural field for a moment to illustrate this with a linoleum roll. There's a company that makes linoleum, and they have to make these rolls because you can't buy those at the hardware store, and that's going to roll the pattern out on the linoleum. This roll is 10, 12, 14 foot wide, depending on what the sheets of linoleum are going to look like. If we look down on the inside of this, it has a big thick end disc and a little stub shaft that comes in and fillet welds inside and out. And then when they put it into service, they find cracks initiating from the weld toe and going into the shaft. I think you can all see what's going on. They have full reversal loading. The shaft is bending somewhat, and they have a stress concentration at the weld toe, and they crack. The weld's in bending. The solution is go to a press fit, put the fillet weld on the inside, leave the weld off on the outside. The cracking goes away. Now, the reason I mention this is in the mechanical field, we don't put our welds into bending a lot, but this illustrates the concern when we would do that. I'm going to skip a couple of examples to buy a little time here. This is the extra wheel on the back of a cement truck. And you load it up with cement, you go out to the job site, you have that wheel back there, usually a hydraulic cylinder that engages it. But this could be any curved beam and bending. It just happens to be from the manufacturer of those units. And they have a box section, outer flange, inner flange, and 2 webs. They put a longitudinal fillet weld. Of course, the fillet weld has to curve around this knuckle area, subject to a bending load, and they find that the fillet weld in this area is cracking. It doesn't take too long until somebody analyzes and figures out what's going on. Here's the bottom flange, and as that's subject to bending, the center of that flange wants to break away. And it's putting this root of the weld into tension, and that's the little example that I gave you before of how easy it is to break welds if they aren't loaded in shear along their throat. So the welder had an idea and said, well, we need to put a weld on the inside. And that's a good idea, but it's kind of hard to get in there. And then the engineer had a different idea, and he said, well, there's an inflection point on a beam subject to bending. If I move these supports in to the point of inflection, I have no relative bending at that point in time. And indeed, that's what was done, and eliminates the bending stress on the weld, and the problem went away. So the principle is don't put welds into bending. Lots of solutions to keep it out of bending. Principle number 3, I've said this before, there are no secondary members in welded construction. There's a problem waiting to happen with this box girder. Somebody specified CJP groove welds in the corner, probably didn't need CJP groove welds in the corner, but they did. Now, if we have CJP groove welds and they're made from one side, we use pre-qualified details, we have steel backing, and here's an interrupted length of backing. Now, the designer didn't consider the backing as part of the structure, but when it's joined by a weld, the backing becomes part of the structure. And so when the box section is strained, the strain associated with this web is the same as the strain associated with that backing. Now we have stress through the backing until it gets to this interface between the two, and whatever stress is in the backing has to bounce out and then continue on. And we have a lack of fusion plane perpendicular to a stress field that acts like a crack. And certainly when subject to cyclic loading, and even in some cases subject to static loading, that's been the source of fracture initiation. Now this is also a code violation because the code says backing needs to be continuous for the length of the joint. The point here is here's backing, no secondary members in welded construction, and something that can be problematic. This is the remains of a boom on a tow truck where exactly that detail was incorporated, where they had two formed channels. The two channels were welded together to make a tube. Steel backing should have run the full length. In fact, they had intermittent lengths of backing along the length, and it was at one of those points of interrupted backing the crack initiated, propagated until one day it hit a pothole carrying some vehicle, and the boom breaks in two. This is a company in Florida that makes big presses to glue together laminated wood arches. So here we see the plies of wood that are being glued together, and this is the hydraulic cylinder. There's a dog that fits into a rack. Now what we need to know is we have a beam that's subject to a bending load when it's loaded up. And now we're going to look at the detail connecting the rack to the beam, and sure enough, there's a crack that's developed into the beam because there's a tack weld or a weld between segments of the rack. Now the rack becomes part of the bending system, right? It's on the outer fibers. So there's bending loads in here until they get to this point, and then the weld constituted the metallurgical path for the crack to propagate into the tension zone of the section. Principle number 4, nothing welds are good for nothing. You said that's not good English. No, but maybe you'll remember it. Now my definition of a nothing weld is a weld that looks like it's full strength, but it's not. Now here's a complete joint penetration groove weld, the way we really wanted it to be made. But this is what the fabricator gave us of a bead on one side, a bead on the other side, and we don't have fusion all the way across. Unless we use some non-destructive testing, looking at these externally, they look the same. But we obviously don't have what we intended to have. That's a nothing weld. I gave you this example earlier where when the welder doesn't leave behind that corner but rather melts it away, we have a nothing weld. It looks like it's full strength, but it's not. Here's a more subtle nothing weld. Here's a good fit-up T-joint with fillet welds of the appropriate size applied. There's the throat associated with the fillet weld with proper fit. What if we have a gap, however? AWS has limits on how far the gap can go. It's 3/16 for most size members, 5/16 for thicker. But if we have a gap, everybody can see that the throat's not what I expected it to be. The throat is smaller than what it should be for a properly fit joint. That's why AWS says if you have a gap of 1/16 of an inch, you're okay. But after that, you need to increase the amount of the size of the weld by the size of the gap. And when you do that, you come back to the proper stress. Now, if you have no gap, you have 21 KSI on the throat. If you don't increase the weld size, you have a 1/16 of a gap, then you have 28 KSI on the throat. If you have an 1/8 of an inch gap, you don't increase weld size, you're up to 42 KSI. And if you have a 3/16 gap, you don't increase the size, you're up to 84 KSI on the throat of the weld. Obviously, you can't tolerate that. But if you increase the weld size by the amount of the gap, you go back to the 21 KSI. Principle number 5, avoid a joint where the strength and performance of the joint detail depends on the skill of the welder. Somebody was mentioning this one to me at break. When we frame tubular members into a truss, please pay attention to the radius that's going to be in the main member. Now, if the thicknesses are about the same, chances are you're going to be able to make this weld and you don't have too much trouble. But more often than not, your main member will be thicker because you need additional capacity in the main member as opposed to the branch member. As soon as you have thicker material, then that radius gets bigger, and I trust you can see that now we have a gap. And this is a gap the welder's going to need to contend with, and if the welder's job is hard, then we don't know what kind of quality we're going to get. It may be possible, or it is possible, to fit some specialized backing in there. That might be a solution. You may build up the corner with some weld metal, grind that off, and then fit it up. That's another solution to the problem. You may specially profile cut that member that frames in. That would be another alternative. But look at how simple it is to go to what we call a stepped connection. If you make the branch member larger than the branch member smaller than the main member, then I can put in simple fillet welds all the way around the perimeter. So that may be a good option for you to employ.